Okay, so let's take a look at our vertical double body worksheet. We pretty much did problem one in class. Here's the pictures again. Our system, our 3 kilogram object, and our 2 kilogram object. Um, and now let's get a hold of number two. And the key word here in number two is constant velocity. Well, if it's constant velocity, then we know we're going to start with the sum of the forces is equal to 0. All right, now we need to find the tension in each rope. So, probably the easiest picture to deal with is the one over here on the right side. All right, and that contains the, rope number 2, right? So if we want to talk about the sum of the forces acting on object number 2, we call it the 2 kilogram object, then it's got to be equal to 0 because of this constant velocity. Well, our two forces are T2 and W2, so T2 minus the weight of 2 must equal 0. And because we have a constant speed, then we know T2 is equal to W2. So T2 is equal to M2 times the acceleration due to gravity, which is 2 kilograms times 9.8 meters per second squared, which is 19.6 newtons. So the tension in rope 2 is going to be 19.6 newtons. Now, we got to find T1, so we could go either here or there. It really doesn't make any difference, right? So let's go here to question number 3. The sum of the forces on the 3 kilogram object must equal 0. So T1 minus T2 minus the weight of that 3 kilogram object must equal 0. So T1 is T2 plus the weight of the 3 kilogram object, which is T2 plus M3 times G, or T1 is equal to T2 is 19.6 newtons, 19.6 newtons, plus 3 kilograms times 9.8 meters per second squared, which would be 49 newtons. For question number 3, we basically have the same situation, except we're replacing the tension force that was in between block 1 and 2 in the previous problems with what's often referred to as a contact force, right? 2 is pushing on 1 and 1 is pushing on 2. So if we consider the system, right, then we've got this force from underneath F. Somebody's hand is exerting this force, and weight 1 and weight 2 are pushing down. Now, if we think about the big object here on the bottom, that hand force is acting on the big object. What else is acting on the big object? The weight of the big object, I'm calling that W2, and F3, I'm calling it, which is, just so we don't get our 1s and 2s mixed up, right? F3 is the force of the top box pushing on the bottom box. That's F3. So what forces are acting on this big box? Gravity's pulling it down, and box 1 is pushing it down. Now, what forces are acting on this small box? Well, the hand doesn't act on the small box because the hand is underneath here acting on the big box. But the big box is pushing up on the little box. Now, I've also labeled that F3 because this and this are an action-reaction pair. They're a contact force pair, an action-reaction pair. The bottom box pushes up on the top box pushes down on the bottom box, equal and opposite. What else is acting on the small box up here? W1. So if you look back on your previous question, really all we're doing is we're swapping this for that second tension force. It's really the same stuff. All right. What vertical force must the hand exert upward? Oh, stationary. So if this stuff is stationary, then the sum of the forces is equal to 0. What vertical force must the hand exert upward? So we're looking for this. And what is the force exerted on a 40 Newton box by the 3 kilogram box? So we're looking for that, that's the same thing, or that and that. Those two things are the same thing. Well, it doesn't make sense for us to go to this picture because it's got two things that we don't know. So if we go to this picture, it becomes relatively easy to get the answer to the force exerted by the 40 Newton box on the 3 kilogram box. So sum of the forces on this 3 kilogram box is equal to 0. What forces are acting there? Well, F3 minus what we call is weight 1 based on that picture is equal to 0. So F3, which is the force exerted on the 40 Newton box by the 3 kilogram box, is equal to W sub 1, which is M1 times G. So F3 is equal to 3 kilograms times 9.8 meters per second squared, or that contact force is equal to 29.4 newtons. What vertical force must the hand exert upwards? That's here or here. Pick your poison, whichever one you want to do. Well, I'm going to say let's do this one since we just found F3. So the sum of the forces here is equal to 0. What's my picture look like? F, which is the thing I want, minus F3 minus W2 is equal to 0. So F, which is the thing we're trying to find, F is equal to F3 plus W2. Well, do we know F3? Yeah, it's 29.4. Do we know W2? Well, we've been substituting M times G for these W's, but we don't have to in this case because this is a 40 Newton box. That's the weight of the object. So then F simply becomes 29.4 newtons plus 40 newtons or 69.4 newtons. Now again, this just shows you, don't get habitual about this. Don't automatically think you got to plug in M times G to get the W. Sometimes you do, sometimes you don't. So question 4 has 5 mirrors. And so it's probably best to draw our system diagram here where I just put W total going down, so we've got action reaction happening in here and here and here and here. We got strings connecting all of these things. All right. So rather than list all 5 things, it's easier for us to say, okay, here's this system. I've got tension in this top rope that is basically pulling up the entire system, and the entire system is being pulled down by its weight. And our first question says, what's the tension force in the top string if the system is accelerating? So we've got our picture. It's accelerating, so sum of the forces on the system must equal the mass of the system times the acceleration of the system. Now we want to find this tension in the top. So we've got to work that in here by saying, okay, the tension in the top rope, T top, minus the weight total must equal the mass of the system times the acceleration of the system. So my total tension here, or top rather, my top tension, T top, must equal then the total weight plus the mass of the system times the acceleration of the system. Well, what's the total weight? Look at what we got here, right? The top 4 mirrors are all the same and the bottom one is different. So in reality here, that top tension has to equal, let's call it 4 times the weight of the top mirror plus the weight of the bottom mirror plus M, mass of the system, acceleration of the system. All right. So do we know the weight of the top mirror? Well, no, but we know that its mass is 1 kilogram. So the tension at the top is equal to 4 times the mass of the top object times the acceleration due to gravity. That's the weight of this top object. 4 times that mass times g, plus the weight of the bottom. Now, do we know the weight of the bottom? Well, we do, right? It's 5 newtons. We got to know that the 5 newtons is the weight. So weight of the bottom plus the mass of the system. So now, do we know the mass of the system? Well, kind of. It's 4 times the mass of the top plus the mass of the bottom. The mass of the bottom is that weight divided by g. So the mass of the system is 4 times the mass of the top object plus the weight of the bottom divided by g. There's the mass of the system times the acceleration of the system. So we're trying to find this. We know 4. The mass of the top one is 1 kilogram times 9.8 plus the weight of the bottom, which is 5, plus 4 times 1 kilogram plus 5 divided by 9.8 times the acceleration of the system, which is 2, gives us the tension at the top. So then our 4 times 1 times 9.8 is 39.2 newtons plus 5 newtons plus 4 times 1 is 4. 5 divided by 10 roughly is a half. So in the parentheses here, I got 4.5 times 2 is 9 newtons. So I've got 14 plus 39. The tension here in the top is going to be 53.2 newtons. What's the tension force in the string that holds up the bottom object while the system is accelerating? Well, my diagram on that bottom object, I'll just put a little b there. That's just the tension in the bottom, T sub b, and the weight of the bottom underneath here. So the sum of the forces acting on the bottom object is equal to the mass of the bottom object times the acceleration of the bottom object. TB minus WB is equal to MB times AB. We're trying to find this tension in the bottom. Well, so that tension in the bottom string is going to equal the weight of the bottom object plus the mass of the bottom object times its acceleration. We know that's 5. We know that's 2. We don't know the number there, but we've got to take the bottom weight divided by g to get us that. So TB is equal to the weight of the bottom plus the weight of the bottom divided by g times the acceleration of the bottom. Probably should just leave it as b there. So the tension in the bottom is equal to 5 newtons plus, basically again, 5 divided by 9.8, 5 divided by 10 gives us roughly a half of a newton. Oh, I'm sorry, half of a kilogram rather, times 2 meters per second squared. That's 0.5, right? Then the tension in that bottom is roughly 6 newtons. Okay, so the last problem is relatively complicated. I only got 1 minute and 10 seconds left on the video, so we're gonna go a little quick, all right? So basically what do we got? We got 4 boxes, box 1, 2, 3, 4. The top box has a mass of m. Each successive other box has a mass of 2m more than the smaller box. So this is m plus 2m or 3m, 3m plus 2m or 5m, and the mass of this one down here is 7m. We're trying to find how much force this 7m box exerts on this 5m box if the forklift is lifting up from below the 7m's. So the trick here is we could do 5 separate diagrams, one for the system and one for each of these objects, but instead if we combined the top 3 objects into one object, then the force that acts on it is the force of the bottom box and the weight going down. So if you take a look at this entity here, the key transitions come in when we take weight, and that's going to be 9m times g, that's our total mass, And the acceleration is actually g over 3.